Welcome to today's session. In this video, we'll be exploring problem number 265, Paint House 2. This problem challenges us to minimize the painting cost of houses while adhering to specific constraints. We'll analyze the problem, evaluate approaches, and break down the solution step by step. Let's dive in. In this problem, we are tasked with painting a row of n houses using k available colors. The cost of painting each house with a specific color is given in a 2D matrix called costs, where costs, I, j, represents the cost of painting the ith house with the jth color. The goal is to minimize the total painting cost while ensuring that no two adjacent houses share the same color. The input includes three components: an integer n for the number of houses, an integer k for the number of available colors, and the 2D array costs that provides the painting costs. The output is a single integer representing the minimum cost required to paint all houses while meeting the constraint that adjacent houses must have different colors. For example, consider n equals 3 houses and k equals 3 colors, with the costs matrix given as 17, 2, 17, 16, 16, 5, 14, 3, 19. Here, we want to find the minimum cost to paint all 3 houses. If we paint house 0 with color 1, cost equals 2, house 1 with color 2, cost equals 5, and house 2 with color 1, cost equals 3, the total cost is 2 plus 5 plus 3 equals 10. This is the minimum possible cost under the condition that no two adjacent houses have the same color, so the output is 10. Now let's look at another example with n equals 2 houses and k equals 3 colors. The costs matrix is 7, 3, 8, 5, 6, 7. To minimize the total cost, we can paint house 0 with color 1, cost equals 3, and house 1 with color 0, cost equals 5. The total cost for this configuration is 3 plus 5 equals 8. Since this satisfies the condition that adjacent houses have different colors, the output for this example is 8. For a third example, let's consider n equals 4 houses and k equals 2 colors, with the costs matrix as 1, 5, 2, 9, 4, 1, 3, 3. To minimize the cost, we can start by painting house 0 with color 0, cost equals 1, house 1 with color 1, cost equals 9, and house 2 with color 0, cost equals 4. Finally, we paint house 3 with color 1, cost equals 3. Adding these costs together, the total is 1 plus 9 plus 4 plus 3 equals 8. This is the minimum cost while ensuring no two adjacent houses share the same color. Additionally, the problem comes with constraints to consider. The number of houses n can range from 1 to 100, the number of colors k from 1 to 20, and the cost values from 1 to 10 to the power of 4. Special cases include scenarios like having only one house, only one color, or all costs being equal. The solution must also handle large inputs efficiently, adhering to these constraints. To solve the Paint House 2 problem, we first consider the brute force approach. The idea here is to try every possible way to paint the houses while ensuring that no two adjacent houses share the same color. For each house, we loop through all k colors, calculate the total cost for every valid combination, and then return the minimum cost. Although this approach is easy to understand and implement, it's highly inefficient due to the exponential growth of the search space. The time complexity of this method is O, k to the power of n, where n is the number of houses and k is the number of colors. This means the solution becomes computationally infeasible as the input size grows. To address this, we move to a dynamic programming approach using a full cost matrix. Here, we define dp, I, j, as the minimum cost to paint up to house I with color j. The key insight is to build the solution incrementally. The cost of painting house I with color j depends on the cost of painting house I with that color, plus the minimum cost of painting the previous house with a different color. Using this recurrence relation, we fill out the dp table row by row. Finally, the minimum value in the last row gives the answer. While this is more efficient than brute force, it still involves redundant calculations, as finding the minimum for all other colors repeatedly results in a time complexity of O, and *k squared. To improve efficiency further, we optimize the dynamic programming approach by focusing on the computation of the minimum cost. Instead of recalculating the minimum for all other colors at each step, we maintain two variables, min1, which holds the smallest cost across all colors for the previous house, and min2, which holds the second smallest cost. For each color j in the current house, if j corresponds to min1 from the previous house, we use min2 since min1 would violate the constraint of adjacent houses having different colors. Otherwise, we use min1. This eliminates the need to loop through all colors to compute the minimum repeatedly, drastically improving performance. The time complexity of this optimized approach is reduced to O, and *k, and the space complexity is reduced to O, k, as we only need to store the costs for the current and previous rows. With this optimization, the approach becomes both efficient and scalable. Given the constraints of the problem, this is the strategy we chose to implement. It balances clarity and performance by leveraging the observation about maintaining the two smallest costs, enabling us to optimize the redundant computations seen in the unoptimized DP approach. Each of the approaches we considered comes with its own trade-offs. The brute force method is straightforward and intuitive, but its exponential time complexity makes it completely impractical for large inputs. The unoptimized dynamic programming approach improves on this by avoiding the brute force search through the entire solution space. However, its time complexity of O, and *k squared, is still inefficient when the number of colors, k, is large. The optimized dynamic programming approach stands out as the most efficient solution, with a linear time complexity in terms of k. By maintaining min1 and min2, we eliminate redundant calculations, making this approach scalable and well-suited for competitive programming scenarios. The main trade-off with the optimized approach is its greater implementation complexity due to the bookkeeping required for the two minimums. However, this additional complexity is justified by the significant performance gain. Ultimately, the optimized DP approach provides the best balance between efficiency and scalability, making it the ideal choice for solving the problem within the given constraints. In this problem, we need to determine the minimum cost to paint n houses using k different colors, ensuring that no two adjacent houses are painted the same color. The input is provided as a 2D array costs, where costs I, j, represents the cost of painting house I with color j. Our goal is to minimize the total painting cost while respecting the condition that adjacent houses must have different colors. To begin, we can think about solving this problem using a brute force approach. This involves generating all possible combinations of colors for the n houses that satisfy the adjacency condition. Once we have the valid combinations, we calculate the total painting cost for each of them and return the minimum cost. However, this approach is computationally expensive, especially as n and k grow large, making it impractical for larger inputs. This motivates the need for a more efficient solution using dynamic programming. To optimize the solution, we use dynamic programming. We start by defining our state. dp I, j represents the minimum cost to paint houses up to house I, where house I is painted with color j. For the base case, when considering the first house, the cost of painting it any color is simply the cost given in the costs array. Mathematically, we can represent this as dp 0 j equals costs 0 j for all valid colors j. Moving forward, the cost of painting each subsequent house depends on two factors: the cost of painting the current house with a given color and the minimum cost of painting all previous houses such that no two adjacent houses share the same color. Thus, the recursive relation becomes dp I, j equals costs I, j plus min dp I1 and c for all c equals j. This ensures that the adjacency constraint is respected while minimizing the total cost. After filling out the dp table, the final result is found by taking the minimum value from the last row of the table, which represents the minimum cost of painting all houses. Mathematically, this is expressed as result equals min dp n1 j for j in range k. To further optimize the solution, we can reduce the space complexity. Instead of maintaining the full 2D dp table, we only need the previous row at any given time, allowing us to overwrite the dp array and reduce space usage from O and *k to O, k. This optimization is particularly useful when the number of houses, n, is large. The brute force approach, which has a time complexity of O, k to the power of n, is infeasible for large inputs. In contrast, dynamic programming reduces the time complexity to O and *k squared by efficiently reusing results from previous computations. This makes it a practical solution for real-world scenarios. Additionally, by leveraging space optimization, we make the algorithm even more memory efficient. The dynamic programming solution uses specific data structures to achieve efficiency. First, we initialize a 2D DP table of size nxk to store the minimum cost for each house color combination. However, we later optimize this by replacing the 2D table with a 1D array that stores only the previous row, significantly reducing memory usage. Regarding complexity, the time complexity is n*k squared, since, for each house, we compute the minimum cost for each of the k colors, and finding the minimum among k options takes k. The space complexity, with the optimized approach, is reduced to k, as we only store one row of the DP table at any point in time. It's important to account for edge cases too. For a single house, the result is simply the minimum cost from the costs array. If there is only one color available, the problem is unsolvable unless there is only one house. For large values of n or k, the optimized dynamic programming approach ensures efficient computation. Additionally, the algorithm must handle cases where the input is empty or invalid, ensuring robustness. Let's walk through an example to see the algorithm in action. Suppose we have n equals 3 houses and k equals 3 colors, with costs equals 1, 5, 7, 5, 8, 4, 3, 2, 9. To start, we initialize dp 0 as 1, 5, 7, which directly represents the costs of painting the first house with each color. For the second house, we calculate dp 1, 0 equals 5 plus min 5, 7 equals 10, dp 1, 1 equals 8 plus min 1, 7 equals 9, and dp 1, 2 equals 4 plus min 1, 5 equals 5, giving us dp 1 equals 10, 9, 5. For the third house, we compute dp 2, 0 equals 3 plus min 9, 5 equals 8, dp 2, 1 equals 2 plus min 10, 5 equals 7, and dp 2, 2 equals 9 plus min 10, 9 equals 18, resulting in dp 2 equals 8, 7, 18. Finally, the minimum cost to paint all houses is min dp 2 equals 7. This corresponds to painting house 0 with color 0, house 1 with color 2, and house 2 with color 1, achieving the desired result efficiently. Here, we start by defining a class solution with a method minCostIA that takes the costs matrix as input. The first step is to handle edge cases. If the costs matrix is empty, we simply return 0 since there's nothing to paint. Next, we calculate n, the number of houses, and k, the number of colors available. If there's only one color in more than one house, it's impossible to paint the houses without violating the problem's constraints, so we return infinity. Now, we initialize three variables, prev_min, prev_second_min, and prev_min_color. These will help us track the indices of the smallest and second smallest costs from the previous house, as well as the color index associated with the minimum cost. For the first house, we determine the initial prev_min and prev_second_min by iterating through the available colors and comparing the costs. This sets up the groundwork for the main logic to process subsequent houses. In the next part, we process each house starting from the second one. For each house, we initialize three variables, cur_min, cur_second_min, and cur_min_color, which are used to track the smallest and second smallest costs for the current house. Then, for each color, we calculate the cost to paint the current house. If the current color matches the color with the minimum cost from the previous house, we add the second smallest cost from the previous house to avoid using the same color consecutively. Otherwise, we add the smallest cost. As we update the costs for the current house, we also update cur_min and cur_second_min by tracking the smallest and second smallest values in the current row. Once the inner loop is complete, we update prev_min and prev_second_min for the next house. Finally, after processing all houses, we return the minimum cost from the last row of the costs matrix, which represents the minimum cost to paint all houses without violating the constraints. Here, we begin by importing the necessary utilities and defining our solution class. The function minCostIA takes a 2D array costs as input, where each row represents a house and each column represents a color option. The goal is to minimize the total painting cost while ensuring that no two adjacent houses share the same color. First, we handle edge cases. If the input is null or empty, we return 0. Next, we extract n, the number of houses, and k, the number of colors. If there's only one color available but more than one house, it's impossible to satisfy the constraint, so we return integer.max_value. We then introduce variables to track the minimum and second minimum costs for the previous house, as well as the color associated with the minimum cost. Using a loop, we initialize these values for the very first house by iterating through the available colors and finding the smallest and second smallest costs. This setup is critical because it allows us to efficiently calculate the minimum cost for subsequent houses without recomputing everything from scratch. Now, we move on to iterating through the remaining houses, starting from the second one. For each house, we initialize variables to track the current minimum and second minimum costs. Then, for each color option, we calculate the cumulative cost of painting the current house. If the current color matches the previous house's minimum cost color, we add the previous house's second minimum cost to avoid using the same color consecutively. Otherwise, we add the previous house's minimum cost. This ensures that the color constraint is satisfied while minimizing the cost. As we compute the cumulative cost for each color, we also update the current minimum and second minimum costs dynamically, keeping track of their indices. These updated values will later serve as the reference for the next house. Once the inner loop completes, we update the previous minimum, second minimum, and their corresponding indices to reflect the results of the current house. This process ensures that we maintain an efficient rolling calculation of the minimum costs as we progress through the houses. Finally, after processing all the houses, we calculate the overall minimum cost. To do this, we iterate through the last row of the costs array, which now contains the cumulative costs for all color options for the final house. We use the math.min function to find the smallest value among these options, which represents the minimum cost of painting all houses while satisfying the color constraints. This value is then returned as the result. By maintaining and updating only the minimum and second minimum costs at each step, we achieve an optimized solution with a time complexity of O(n*k), making it efficient even for larger inputs. That wraps up the implementation of the min_cost_ii function in Java. To solve this problem, we start with a simple example where there are two houses and three available colors. Here, the input matrix costs represents the cost of painting each house with a specific color. The first step is to initialize some variables. N is the number of houses, which is 2, and k is the number of colors, which is 3. We also set prev_min, prev_second_min, and prev_min_color to -1 initially, as placeholders for tracking the minimum and second minimum costs and their respective color indices. Now, for the first house, we traverse through each color and calculate the minimum and second minimum costs. For color 0, the cost is 1, so prev_min gets updated to 0. For color 2, the cost is 3, so prev_second_min becomes 2. After processing all colors for the first house, the minimum cost is associated with color 0, and the second minimum is associated with color 2. For the second house, we repeat a similar process. This time, we use the prev_min and prev_second_min from the first house to compute the new costs. For color 0, since it matches the prev_min_color, we add the second minimum cost from the previous house, which is 3. This updates the cost for color 0 to 5. For color 1, we add the previous minimum cost, which is 1, resulting in a total of 10. Similarly, for color 2, we add the previous minimum cost, updating it to 5. During this process, we also track the new minimum and second minimum costs for the current house. The final costs for the second house are 5, 10, 5, and the overall minimum cost to paint all houses is the smallest value in this row, which is 5. Now, let's consider an edge case where there is only one house. Here, the costs matrix has just one row, and n is 1. Since there's only one house, we don't need to calculate anything further. The solution is simply the minimum cost from this single row. In this example, the costs for the available colors are 7, 2, 4. The smallest value is 2, so the minimum cost to paint the house is 2. In a larger example with 3 houses and 4 colors, we begin by initializing n as 3 and k as 4. From the first row, we identify the minimum and second minimum costs, which are associated with color indices 0 and 1. For the second house, we calculate the new costs by adding either the minimum or second minimum cost from the previous house, depending on whether the color matches the previous minimum. After processing, the updated costs for the second house are 9, 7, 5, 3, and the new minimum and second minimum values are tracked. Then, for the third house, a similar process is followed. Using the updated costs from the second house, we calculate the new costs as 12, 13, 4, 6 for the third house, and we track the new minimum and second minimum values. Finally, the smallest value in the last row gives the minimum cost to paint all houses, which is 4. The result for this example is 4, which represents the minimum cost to paint all houses while ensuring that no two adjacent houses share the same color. This concludes the walkthrough of the solution, demonstrating how the algorithm efficiently calculates the result by leveraging the minimum and second minimum costs at each step. To analyze the time complexity of our solution, let's start with the initialization step. In the first loop, we iterate through all k colors to determine the two smallest cost values for the first house. This step involves only a single pass over the k colors, so it takes k time. Next, we move to the main dynamic programming loop, where the goal is to calculate the cumulative cost for painting each house. For the remaining N1 houses, we iterate over all k colors, and for each color, we compute the cost by either referencing the minimum or second minimum cost from the previous house. This computation is constant time, 1 per color. Additionally, within the same loop, we track the new minimum and second minimum costs for the current house, which also requires 1 per color. Since the inner loop runs k times for each of the N1 houses, the overall contribution of this step is N1 * k, which simplifies to N * k for the main loop. Now, after the loops are complete, we finalize the computation by finding the minimum value in the last row of the costs matrix. This step involves iterating through all k colors in the last row, which takes k time. When we combine all the steps together, the initialization step contributes k, the dynamic programming main loop contributes N * k, and the final computation step adds another k. Since N * k dominates the other terms, the overall time complexity of the solution is N * k. This makes our approach efficient given the constraints of the problem. Turning to space complexity, our solution is designed to be highly space efficient. Instead of creating additional data structures, we modify the input costs matrix directly to store the cumulative costs as we calculate them. This ensures that no extra memory is used for storing intermediate results. The space usage is therefore determined by the input costs matrix, which has dimensions nxk and is already provided. Additionally, we maintain a small, constant number of auxiliary variables such as prev_min, prev_second_min, cur_min, and cur_second_min to keep track of intermediate results during computation. These variables do not depend on the size of the input and remain constant regardless of n or k. As a result, the space complexity of the solution is 1, meaning it uses constant extra space. When we compare this optimized solution to a naive approach, the difference in efficiency becomes clear. A brute force solution would involve trying all possible combinations of colors for the n houses while ensuring no two adjacent houses are painted the same color. For each house, there are k color choices, resulting in k(n) total combinations. Additionally, we would need to validate each combination to ensure it satisfies the adjacency condition. This results in a time complexity of k to the power of n, which grows exponentially and becomes computationally infeasible for large inputs. By contrast, the optimized solution leverages dynamic programming and minimizes redundant computations by tracking only the minimum and second minimum costs. This reduces the complexity to N * k, a dramatic improvement over the naive approach. Moreover, the algorithm's time complexity remains consistent, as it only depends on the dimensions of the costs matrix and not on the specific values within it. This means the best, average, and worst-case scenarios all have the same complexity of N * k, making the solution both efficient and predictable. When solving this problem, there are several common mistakes to watch out for. First, failing to handle edge cases can lead to incorrect results. For example, scenarios where there are no houses, or only one house, should be explicitly tested with cases like n = 0 or n = 1. This ensures the solution is robust and doesn't break in these corner situations. Next, in dynamic programming approaches, recomputing overlapping subproblems without memoization is a frequent issue. This can unnecessarily increase time complexity, so make sure to store and reuse results of overlapping subproblems. Additionally, improper handling of constraints can cause trouble. For instance, assuming k, the number of colors, is always greater than or equal to 3 might lead to errors when k equals 1 or 2. Constraints should always be explicitly verified and addressed in your logic. Another common pitfall is confusing the minimum cost transitions. It's easy to accidentally allow adjacent houses to share the same color, so double-check that your transitions respect the constraints. Finally, inefficient space usage is another area to optimize. If you're using a full 2D DP array but only need the last row, this can unnecessarily consume memory. Instead, reduce the space to store only what's needed, like a single row, to make your solution more efficient. Now, let's consider some key insights for interviews. A strong approach starts by clearly outlining a brute force solution and then systematically optimizing it. Interviewers value your ability to simplify and reduce complexity, so this progression demonstrates strong problem-solving skills. Also, always remember to test edge cases during interviews. Proactively discussing edge cases not only ensures your solution works correctly but also showcases your attention to detail. When explaining your approaches, it's important to highlight trade-offs. For example, you might mention that a 2D dynamic programming solution is easier to implement but consumes more memory, whereas a space-optimized approach trades readability for efficiency. Being able to clearly articulate these trade-offs is a skill interviewers greatly appreciate. Additionally, recognize patterns across related problems. Many problems involving houses, paths, or grids share similar characteristics, like minimizing costs or avoiding conflicts. Identifying these patterns can help you structure your approach more effectively. For related problems, take a look at examples like LeetCode 198, House Robber, which focuses on maximizing value while avoiding adjacent conflicts, or LeetCode 213, House Robber 2, which adds a circular condition to the problem. Similarly, LeetCode 256, Paint House, is a simpler version of this problem with k equal to 3, and LeetCode 931, Minimum Falling Path Sum, explores minimizing costs along paths in a grid. Finally, let's explore some alternative approaches to solving this problem. A brute force method would involve trying all possible combinations while ensuring constraints are satisfied. However, this approach has a time complexity of k to the power of n, making it impractical for large inputs. While it's not efficient, brute force can be useful for understanding the problem and validating optimized solutions. A more practical approach is the 2D dynamic programming method. Here, you define a DP table where DP, I, J, represents the minimum cost to paint up to house I with color J. This solution has a time complexity of n times k squared, and can be further optimized in terms of space. Instead of maintaining a full DP table, you can implement a space-optimized version, which reduces memory usage by storing only the previous row. This brings the space complexity down to k, making it ideal for scenarios where memory is a concern. Lastly, there's the possibility of using a greedy approach, though it's generally less reliable. Greedy strategies might work in certain variations of the problem but often fail when overlapping constraints are involved. If you choose to explore a greedy solution, make sure to verify its correctness thoroughly before relying on it. Great work! To summarize, we addressed problem number 265, Paint House 2, by analyzing the constraints and exploring solutions. We highlighted how dynamic programming can optimize performance and discuss trade-offs between time and space. Thank you for watching, and stay tuned for more problem-solving content. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!